Okay, hello. My name's Josh Sherbrooke. I work on Autonomy at Stoke Space. And yeah, so if you want to control a complex and tightly coupled system, especially one that operates on pretty quick timescales, inevitably you're going to need to automate that behavior. And then if you want to do that at scale, whether by volume, you have 7 of these fancy engines on the bottom of your rocket, or by rate, you want to launch once a month, once a week, once a day. Really leaning into that autonomy becomes a real motivator. So yeah, we're going to look at sort of the feature arc for a young launch company that wants to get to a place where we can wake up, click go, and launch a rocket a few hours later. So let's start by looking at the stage 1 engine, Zenith. Get some sound on this. Okay, so what is happening in this video right now? So the last time that an operator clicked anything was about a minute ago, sequence start. We asserted some initial valve states, started pressing up our run tanks, opened some run lines, proceeded with final chill, engaged an igniter, introduced fuel and ox into the engine, activated control loops, and now we're monitoring for any condition violations of red lines to abort early. But assuming that doesn't happen and we reach duration, goes for a long time, I guess. Eventually shuts down either way. So yeah, what actually went on here? There's some elements of deterministic linear sequencing in time. We want to sequence our startup and sequence valves. And then there's also some state awareness. We talked about red lines for early aborts and control loops. So we can start by asking, is this one-click launch autonomy? And the answer is certainly not. The engine auto sequence is really the simple case. It's fairly deterministic, fairly linear. And we took quite a few manual steps to get to a point where the operator could click go on this sequence. But what we want to do is consider this sequence as one block of autonomy that we're going to combine with many other blocks of autonomy and create a coherent picture of what needs to go down on launch day. And also one that becomes a little bit more resilient to anomalies and the unexpected. So let's look at this arc by going back in time a little bit. Launch minus 4 years. Hardware people say, we need software. We hire Chris, and he says, we're going to build software. It's going to do many things and be highly configurable. It will run on the test stand and the vehicle and the hill, and we're just going to tell it what hardware to talk to. We end up with an architecture that looks something like this. These boxes are flight computers. You can arrange them how you want. You can configure them to talk to various pieces of hardware and run at different cycle rates. The information propagates left up the tree towards ground software, which in this first iteration is Python. Chris did a talk on this last year. And that is originally where the autonomy runs, on the ground software node. So we fast forward a year, hardware shows up. We have software drivers that can talk to that hardware, and we have our first attempts at sequencing things on that hardware. So the easy first thing we want to do is fire a thruster. This is pretty much open valve, turn on igniter, reverse that action. You can add some pumps to that, and you have a actual rocket engine. We'll get to that picture in a second. But I want to emphasize here from the start, the test engineers and the REs are the ones who are actually writing this automation. We have a very simple Python interface that just defines sequencing. And it's not the vehicle software devs that are actually writing the sequence. It's the people who know their hardware context who are owning that. So yeah, we put some thrusters together and we get a really cool looking engine. So what next? So fast forward a year, Hopper. This is our first flight vehicle prototype. It looks a lot like a simplified version of our second stage. And the goal is just to do a brief hop test in Moses Lake. This is where we first start running into some of the limitations of the existing simple autonomy that we have. It's a much more complex system. It's kind of like you're flying the entire test stand and your margins are a lot thinner, and getting yourself into the run box is actually fairly challenging here. And simple linear sequencing wasn't enough. So because this was all in Python, we got to do some hacking and put together state machines to do things like fill our propellant tanks, get us into chill, et cetera. And this worked well enough. We were able to test it on hill and on the vehicle. But we were kind of surpassing what the tooling allowed us to do validation-wise, and it became a little bit harder to test these things than we wanted. Because all of the software is the same and configured differently, we can run the same sequences on the test stand, on the vehicle, on hill, so we can test these things. We can test the autonomy easily. It's just hard to validate. And then I'm going to hand wave Simulink here a lot because that is, we're going to sort of draw an interface between GNC, but I just want to acknowledge there's Simulink running on the vehicle. What does that unlock? We get to do this. It worked, huzzah. And we learned a lot of lessons along the way. So naturally, this is the point at which we rewrite the entire stack in Rust. So now let's fast forward to right around now. And I want to emphasize here, this is a broad strokes technical maturity L-1 year. I'm not talking about schedule. But what's going on, what's new? So we have frequent testing happening on multiple programs. So we might have a stage 2 and a stage 1 hot fire happening multiple times a day in the same day. The autonomy cases that we are building are much more interesting and diverse. Not only are we doing engine hot fires, but we're acceptance testing our avionics boards in Kent with sequences. Our state machines are getting more exciting. We're starting to do things like automating propellant transfers on the stand, and that's not linear at all. It's much more in the if this then that paradigm. We start to sequence sequences with sequences using the software to test the software. And even the familiar hot fire style sequences become more interesting. And part of the reason for this is that the first engine we built, the stage 2 engine, is an expander cycle. So you might have a fairly rigid start sequence, but once it's going, you can pretty much just leave the valves where they are and it'll run. With our first stage engine, it's full flow stage combustion. You need to run a very tight control loop on that. And if you were to just hold the valves in a position, the failure modes would be spectacular. What else is new? Validation and visualization. As we expand the cadence and the kinds of autonomy we're doing, proving that it will work and not crash the software is now just a baseline need. Visualization is key as well. We have more people working on this autonomy, and even folks who didn't write it, who need to understand what's happening while it happens. So console visualization becomes a big player here. And yeah, more REs writing more autonomy. We have, I think now, almost 50 deployments doing completely different things every day. It's very exciting. We get more cool pictures like this. So this is great. We're doing a lot of really cool stuff, but we start to hit this problem. It's too slow. We have about a 15-minute turnaround from you discover a problem, you change the sequence, you run the sequence. And maybe this sounds incredibly slow, maybe it doesn't, but it is when you are paying people who are very smart to sit in a control room and wait for your software to finish building. So this was one of our first lessons in we need to be brutally rigorous with not bloating our dev loop time. It is not acceptable to be faster than about 5 minutes for us. So we got an intern, made that faster. It's great. So now things are in an okay state. We're sort of right around today. Let's take this breathing room to sort of look at what's actually happening in the autonomy stack. So this is a state machine. We're talking about state machines today. It's a very simple one. We open a valve, we wait for a condition, and we close the valve. Here is a slightly more useful state machine. So we're going to open our valve, wait 1/10 of a second, engage the igniter, wait 10 seconds, and close the valve. If at any point we exceed our pressure transducer red line, we'll call it, we're going to abort early. And incidentally, this is an unsafe piece of automation. It's forgetting something. And we'll fix that engage the igniter step in the next slide. But I left that in there to sort of emphasize that that's why it's really important to have your system owners who are actually cognizant of the context of what these actions are doing, writing the autonomy in the driver's seat. So how would we describe this state machine? What's like the simplest interface we could use to build up this information? We need something to create states, do actions, and connect states by transitions. So let's use Python to try and build the state machine. So we're going to add 3 states here, do the actions in the state machine, and then link them with transitions. The first 2 are just our time transitions, and the second 2 we'll consider our red line transitions. This is great. It gets us our state machine. It works, and it lets us describe kind of arbitrarily complex state machines. But really what the engineers are trying to do here is build a piece of automation that feels linear and then can do some special stuff. So we'll add some syntactic sugar and try and make this a little bit cleaner. So we'll start by defining a red line that's going to insert transitions from any non-abort states to the first abort state. We can introduce our transitions in line with the blocks, and we're kind of managing context, so we don't have to use the block variables to talk about them, and we'll know that we're going to apply any of our set action commands to the last block we created. So now we kind of have these 2 flavors of writing state machines, one that's focused on the linear process and one that can be whatever you want. We're running the same software in so many different places, and some of it looks a lot like other bits of it. So you have a hill and you have a test stand. So what we're going to do here is take this Python code and generate 2 versions of the sequence, one that can run on the hill, one that can run on the test stand. So I'm going to go ahead and commit my sequence. We're going to run it through CI, and what do we get? Poorly formatted title, in fact. But we have what's called a dispatch. This is just a TOML representation of our state machine. And then on the right here, we have what it looks like on console when you visualize it. This is going to go up and live in Artifactory, and then we'll see how it can run next. I just want to call out the query side of this. So Noah had a great talk on Monday. We have a lot of data. We want to ask questions about it. And it's not just post-test that we care about what's happening in the data. It's also for these transitions in our state machines. So it is called Stokel. It looks a lot like SQL. And we can ask questions about a single element. We can look at persistence. Remember, the sample rate of our data may be asynchronous to the control cycle rate, so the persistence here matters a lot. And then you can chain things together in ways that tell you useful things about your system. We make a dispatch, we validate it. Now, when I'm saying we're validating the dispatch, that is the thing we're running. That is a source of truth that is being generated from Python, but we're validating this TOML. And we're asking, do the elements exist? Do the queries load? Is there an abort? Can we prove that it will terminate? And is anything that's time-based in order? We're not asking, did you remember to turn off the igniter? We're not asking, will it blow up the hardware? That is, again, why the REs need to have ownership over this. We do a bunch of other fun things as well, including post-log automation, dry running. You could specify one sequence, test your sequence. For example, I might want to run the engine auto sequence without red lines when I modify the actual engine auto sequence. And then we can even do cool stuff like Noah made a tool where you can take your updated set of red lines, plot them against an old test run, and see if you're in violation with your sequence updates. So there's a lot of fun ways that we can try and validate and look at what the expected behavior is going to be. Finally, you're on console, you're an operator, you're going to pull down the dispatches from Artifactory, load it, and run it. And what's actually happening in Rust on the flight computer when it ingests this TOML is very simple. We're just looking every cycle at, are there any transitions we need to go do the actions. Around this point is a great moment to ask, okay, why not just use a domain-specific language for this? There's a lot of ways people describe autonomous behavior. And I think my brief answer to that is that we're really focused on creating an ops framework for Stoke. The use case matters a lot, and it's important that we have control over the notion of what is an abort for Stoke, what is a red line, how do we talk about element state, how do we interface with config and validate that. So we're really trying to find the common set of functionality that we need for all of the integrated hardware testing at Stoke. And that's why, to us, it makes sense to build our own thing. So today, Stoke Autonomy is this state machine generation language that we just looked at. It's live in post-test data eval, configurable control loops and calculations. We're kind of going to hand wave that for today, although you can imagine that there are some things where a state machine is probably not the easiest way to describe it. Like if you want to have a PID loop, building that out of a state machine would be a little bit verbose. Validation, visualization, and then major coming up is the spoofing and sim side of things. You really want to do everything you can to test this like you're actually going to test it on hardware. So is this enough for Flight 1 today? And the answer is no, not quite, but we're getting close. So there are some launch-specific concepts that we need to flesh out a little bit. How do holds work? How does alerting work? Can you take a control transition and demote that to an alert that shows up on console or Slack? Building syntactic sugar in ways that are useful for our launch case. And then finally, and this is the big one, this is going to be the big lift, is a fluid sim-backed testing pipeline. We need to be able to exercise our state machines in plausibly flight-like ways. It's not the design analysis. It doesn't have to be perfect. And hopefully it's better than just forcing state machines into different states. But we want to have some model of the vehicle that's running in hill or locally on SIL that you can say this, I'm going to click the sequence start and it's going to work pretty similarly to the vehicle, and we can train operators that way. Moving into the future now, L minus 6 months. So at this point, we would expect to have a sensor actuator list for the vehicle locked down. Hill is thriving. We're doing a lot of testing, both in hardware and software. We're getting into the major integration tests like stage 1 and stage 2, stage tests, propellant load, things like that. And the actual vehicle automations at this point should be well underway, reaching maturity. So we have things like power up and self-tests, commodity loading, terminal count, and then the flight state machine. Looking ahead 1 month out from launch. At this point, hopefully, all the automation is in a place where we believe that it's done, and we have simulation and testing that is going to convince us that we're ready to go. We're going to ship this thing and it's going to work. And inevitably, it won't the first try. So this is where it becomes incredibly important to be able to be flexible with the autonomy, to fix these problems and have high confidence in that change cadence. Additionally, there's going to be people all across the company now who care exactly what who care to know exactly what the autonomy is doing. And maybe they're not as familiar with the authorship interface. So we need really good visualization tools here just for people to know what's going on. Eventually, you're ready to launch. And it looks something like you have a master mission executor, which is sequencing all of these things that we've talked about, commodity load, engine state machines, things of that nature. Again, inevitably, this is Flight 1 we're talking about, so we'll be resolving anomalies. We'll have holds. We'll need to modify red lines. No matter how much somebody tells you the red line won't change, it will. So we need to be resilient to changing these sequences up until right before launch, if required. And then, yay, hopefully you have a great day. You fly your rocket. So is this one-click launch autonomy? And again, the answer is certainly no. I even said we're going to have anomaly resolution and holds and things of that nature. The goal of this Flight 1 autonomy is to keep us moving through the day and progress to a stable state where we can go solve the problems that we didn't know to expect. So looking forward, launch after launch, all these bullets are pretty much picked from other slides. We want high change confidence, more fault recovery, language constructs that work, and a system that works for system owners to actually write their own autonomy. So I've spent like 20 minutes talking about dev tooling and an iteration loop, and not a whole lot about like what is the one-click launch autonomy for Stoke Space and what flight will that be. And that's because I believe really strongly that to get to one-click launch autonomy, that's not a software team deliverable. Maybe if you had perfect requirements from the start, you could just go and build that. But really, you get that as a product of an ecosystem that allows system owners to effectively define the behavior of their systems and iterate quickly. And eventually, that iteration slows down, and the operator intervention becomes smaller and smaller, and you realize, okay, we clicked one button today, and it worked. So that's where we're going. Thank you for your time. Happy to take questions.
Hey, thanks. That was really cool. I'm curious, are you planning on using this for the flight state machine, or is that a completely different system?
Largely, yes. So there's some interface between GNC running a Simulink and other things that are happening on vehicle subsystems. Generally speaking, GNC is going to drive the rocket and command bits of autonomy and state machines to do certain things. Does that answer your question?
So it sounds like you are saying that this like Python state machine tool is being used on the rocket during flight?
Yes, but remember, we're not running Python on the rocket. We're using Python to generate TOMLs that are executed in Rust.
Great talk. It was really awesome. I was wondering if you could talk a little bit about like when you have all these different sequences and state machines running on a bunch of different systems, how they kind of synchronize with each other, and like if one of them goes into an abort state, how that gets kind of propagated to the other systems.
Yeah. So generally speaking, the interface for all of our software modules, including the Autonomy, is through elements like a pressure transducer, but for software things. So you can look at other state machine state from any other state machine. I think probably the most interesting problem that we need to go solve a little bit better is like resource contention. If you want to guarantee that like one valve can't be stepped on by another state machine. But generally speaking, all of that state is like pretty globally visible within the flight computer at least.
Can take one more.
This is on. This was really neat. Thank you so much. For many years when I was at APL, I worked on something almost identical to this. And actually about 10 years ago, had a similar presentation. But my first question, whenever I see finite state machine-based control, once you have that representation as a graph, then you can start to apply all sorts of formal methods to it. So have you taken any requirements or constraints or anything like that, encoded those, and then used a model check or some kind of tool to make sure that it works correctly?
I don't know if I have a great answer to your question, but I'd like to follow up after. I think in most cases, the kind of behavior that we're describing has to do with like a system owner being able to like trying to coax a hardware engineer to draw the desired behavior of their system into a state machine. And generally, I don't think we want to like optimize or shuffle that around more than what they want it to do. But I'd love to follow up after.
All right, was there one more? Yeah, go ahead.
There was a, probably it's a typo. I think you said something like a test like you test. Is it test like you fly, right?
No, I meant that one. And I say that because for the foreseeable future, our flights are our tests, and our tests look a lot like flights. There's no like hard distinction between a test stand and a vehicle. And Hopper was a flight and it was a test. And I think what I want to emphasize is like having extreme consistency between the way that you define software behavior for any regime of hardware or like integrated software testing is desirable.
Okay, thanks for the clarification. Can I just better understand what is the mission assurance posture at Stoke Space?
Go for it, Chris.
Yeah, sure. I mean, we're a young launch company. I think that we're in the same boat as many of the other launch companies, right? I'm not going to promise you that we're going to deliver something on the first try, but we are going to work through that as we like understand more and more of our vehicle. Once we get to actually sending customers to orbit, then we will have a launch assurance posture of like, hey, this is like, we are selling you a ride, right? But until then, we're testing, right? That's iterative cadence, right? Like we're not trying to take on some like DO-178 or anything like that as the start. We are trying to build a very, very complex system very, very quickly and kind of like work through those hurdles, right?
Thanks, Chris.
All right, thank you, Josh.